Now, so how did this theorem work? So, basically this the Nechiporak's theorem, this works by restricting the function domain. Okay. So, we kind of give a lower bound by looking at the number of sub functions on a smaller domain, and we consider all such possible combination, or I mean all such possible subdomains that we have, all these yi's that we have, and we count all the sub functions over these yi's, and that gives us this theorem. Right. Now, what about if we try to extend this idea? Okay. So, what happens if we try to extend this idea of restriction and see what other kind of lower bounds we can achieve? Okay. So, this is actually a very powerful idea, and as we shall see that many different lower bounds were obtained by exploiting this idea of restriction. Okay. So, one point here is that in Nechiporak's theorem, the basis was B2. Okay. In other words, we could not use any information about the gates inside the formula. Okay. So, those gates can be any formula, or I mean it can be any function on two variables. Okay. But what if, let us say I have the basis as the Demorgan's basis? Okay. What if I have the gates only as AND, OR and NOT gates? Then can I actually give maybe a different lower bound? Okay. So, let me just try to formalize a few things, and then I will come back to this question. So, once again let me give the definition of restriction slightly differently. Yeah, so I will be using this definition actually. Yeah. Okay. So, let f be a function and a partial assignment is a function, let us call it sigma, from 0 1 to the power n to 0 1 and some symbol star. Okay. Yeah. So, this is what a partial function means, and just to understand the meaning of this, here star means that the corresponding indices are unassigned. Okay. So, in other words, the indices which go to 0 and 1, they are getting a fixed value. Okay. So, they are getting a fixed assignment, and the indices which go to star, they are free. Okay. So, this is another way of looking at a restriction, and the notation that we use is that the same notation. So, here f restricted to sigma is the corresponding restriction. So, again f restricted to sigma basically is a function on the variable set which is going to star, okay, because all the other variables are taking a fixed value, either 0 or 1. So, now I will define this set R n m to be all functions sigma going from 0 1 to the power n to 0, 1 and star. So, all such partial assignments such that if I look at F inverse of star. So, what is F inverse of star? What is this? All the indices. Okay, so, these are indices which are going to 0, 1 and star. So, all the indices which are unassigned, right. No, not F, sigma. Yeah, this is not F, this is actually sigma inverse, correct. So, sigma inverse of star is basically all the assignments which are unassigned, all the indices which are unassigned. So, when the size of this is equal to m. Okay. So, essentially all partial assignments which leave m indices unassigned. Okay. Huh? Sigma inverse. Sigma 0, 1, so this is basically a partial assignment. Sigma is a partial assignment which is taking 0, 1 to the power n to 0, 1 star, such that the size of this set is m. There are n indices. I mean, the number of indices is n, the number of ways in which you can pick those subsets is 2 to the power n, possibly. Right. But what I am saying is that from those n indices, look at those for a fixed sigma. Once I fix a sigma, okay, it is sending a fixed number of those indices to star. Okay. So, I am just counting that how many such partial assignments are there where the size of that set is equal to m. Or not counting how many, yeah, that, yeah, basically, yeah. So, all the partial assignments which is taking it to m. Maximum value of m can be n.
What is the meaning of this writing this function? So, I mean, when I am saying 0, 1 to the power n, so then there are 2 to the power, I mean, aren't there 2 to the power n combinations of?
No. So, let us say I have one sigma, so I have let us say a sigma which is a function from this to this. I can have another function tau which is going from this to this, another function I can have maybe something else which again going from this to this. And suppose let us say that for all of those, the number of indices which are mapping to star is equal to m. Okay. So, each of those functions will belong to this set then.
Should the domain of sigma be the variable set instead of all strings?
The domain of sigma is the, no, it is basically the all strings.
Then the domain is of size 2 to the power n.
Yes, the domain is of size 2 to the power n, yes.
So, out of these 2 to the power n, some are mapping to 0, some are mapping to 1, some are mapping to star.
Out of all those, no. See,
So, that is the meaning of a sigma writing like this, it's like this.
so the domain of sigma is a string. So, the number of elements in the domain is 2 to the power n, correct. Now,
When I am saying sigma is a domain and the range is 0, 1 star.
yes,
That means we are writing these 2 to the power, if I write a truth table, then there are 2 to the power n assignments.
yes,
And for each one I am writing 0, 1.
0, 1 star, right. Now, look at the, in that truth table, look at those rows where you have a star on the rightmost column,
Yes.
okay.
Take all those rows.
And you take all those rows, correct.
Yes.
If the number of those rows is equal to m,
Yes. So then m can be 2 to the power n, because there are 2 to the power n such assignments.
yeah, so did I make, it is true. Yeah, so actually I do not want it to be this way. So, Yeah, exactly. So, what I want is that each index to go to 0, 1 or star, not each string to go to 0, 1 star. Yeah. So, basically I can write this as follows. Yeah. So, this is not the correct way to write it. So, we should write this as sigma from this set to 0, 1 star. You are right. Yeah. So, this I think I had a mistake. So, it should be from n to 0, 1 star. Okay. So, where this is the standard notation. So, this n in box bracket means the set 1 to n. Yeah, actually this is what I was saying also, that basically this is a function which is mapping these indices to 0, 1 star, okay, not all string to 0, 1 star. Yeah, that is a good point. Okay, so now is it clear? So now what else do I need? Okay. So if we choose a sigma uniformly at random, okay, so note so let sigma be chosen from R and M uniformly at random, what can we say about the expected size of L of F restricted to sigma in terms of the size of F? Okay, let us try to understand the meaning of this thing over here. So, if I choose a random restriction, okay, a restriction which is keeping m indices unassigned, everything else is fixed to either 0 or 1. Okay. And now I want to compare these two things. Okay. So, now for that I get a corresponding function f sigma, and I am counting what is the formula size or the leaf size of that function. Okay. Because this is a randomly chosen element, I can look at the expected size, okay, what is in average, what is that size, and now I want to compare that with the size of the formula f, or what is the leaf size of the formula f. How much should it be? How does these two things compare? So, first of all, is this bigger or smaller than this? Huh? Why is it smaller? It is restricted. Okay, so some of the variables are getting a fixed value 0 or 1. So, the formula size of course becomes smaller. Now, the question is how much small does it get? Okay. So, so it depends actually on this value m, which means that how many are restricted. Okay. So, let me write m as some epsilon times n. Okay. Let us say that where m equal to epsilon n, okay, for some epsilon less than 1. So, some epsilon fraction of the variables remain as they are. So, 1 minus epsilon gets set to 0, 1. Then what happens? Okay. So, if for every leaf, okay, so for look at a variable xi. Okay. So, if that xi appears some li number of times, okay, and if that xi is set to 0 or 1, then here the size of that formula will basically decrease by li. Okay. So, in other words, if epsilon fraction of this basically epsilon fraction of the variables remain, then the size of this formula, the expected size of this formula will be epsilon times this L of f. okay, because it is basically just counting. I mean, it is just counting the number of leaves that remain. Okay, so exactly those variables would become would vanish, the ones which are set to 0 or 1, and the ones which remain will be the variables which remain over here. Okay. So, this is something that is easy to see, but here I am not using any structure of the formula. Okay. If you just look at this observation over here, this note over here, this is just saying that okay, if I had, let us say, a tree which has some L leaves, okay, and if I take some k of them and I set to 0 or 1, then in the remaining tree I will have whatever, what did I say, t minus L, whatever it is, that many leaves remaining. That is all I am saying over here, right. But what about the internal structure? But this is not just an arbitrary tree. Okay, this is a tree which is a formula, which means that the internal nodes are AND, OR and NOT gates, because the question that I posed at the beginning is that instead of B2, what happens if I work over the Demorgan's basis. Okay, so let me write that over here. So, what happens if we consider formulae over the basis and or and not. Okay. The reason why, let me just spend some more time to motivate this point. The reason why this becomes interesting now is because, so consider a situation where let us say that I have a AND gate, okay, and it has one leaf over here and it has some subtree over here. Okay. Let us say this leaf was a variable some xi and I have some subtree over here. Now, what happens if this variable gets set to 0? Does the size of this subtree matter anymore? It does not, right, because this is an AND gate, irrespective of what values you assign to the variables present over here, this entire thing becomes 0, this function, right. So, assignment of values to certain variables depending on what their parent gate is might make the formula size even smaller. So, here when I gave this upper bound, I was not considering any such special case, or not special cases, but any such structure of the formula. Okay. But if I look at this Demorgan's basis, then actually I can consider such structures. Okay. So, the question is how can those structures be considered and how can those structures be exploited to get a better lower bound. Okay. So, that is essentially the motivation. So, any questions? Okay. So, what we will show is something like this. So, what we will show, let me just very informally state this over here, because this will take some time. Okay, maybe I can just state the theorem itself. So, we will show that, so this theorem was by another mathematician known as Subbotovskaya. So, what he showed is that if we have a function f from zero 1 to the power n to 0 1, then the expected size of so the expectation is over, I choose a sigma from R n epsilon n, okay, uniformly at random. and the leaf size of f sigma is bounded by epsilon to the power 1.5 times the leaf size of f plus plus 1/3. Okay. And here I did not write the basis over here, let me write it over here. Over the basis and or not. Okay. So, let us try to just compare this with this over here. This was our initial observation. So, observe that here we have a factor of 1.5. Okay. So, this is basically a smaller number. Okay. So, we get a better upper bound. Okay. So, how do we prove this? Okay. So, I will not be getting to the entire proof today, but before getting to the entire proof, let me just prove one of the main components that is used in this theorem. So, lemma. So, let L of B greater than 1. Let us say we have a formula size whose number of leaves is greater than 1. Then E sigma uniformly chosen from R n n minus 1 L of f sigma is at most 1 minus 3/2 of n times L of f. Okay. Let us try to prove this result. So, what this is saying is that if I randomly assign, so basically if I fix one variable, okay, if all the n minus 1 variables remain unassigned, if I just fix one variable randomly, then the resulting formula size would be upper bounded by this quantity. Okay. So, how do we prove this? So, to prove this I will use just one more claim. Okay. So, once again, so before proving this, so what happens if we do this over a general basis, not over the Demorgan spaces? So, what happens if I fix one variable to 0 or 1? It means that every occurrence of that variable now vanishes, right? Every occurrence of that variable now goes to a fixed 0 or 1, right? So, so what is L of f? So, L of f I can write as, so let Li be the number of occurrences of xi. Okay. So, what is this quantity? So, expected value of L f sigma is nothing but I sum all these quantities. So, basically if I fix one particular variable over here, what I get is one second, let me just how can I write this? So it is LF minus LI sigma LF minus LI, yeah. So it will be sigma L of F minus Li I going from 1 up to n. Correct? So, essentially what I am doing here is that let us take the first variable. Okay. So, if I fix the first variable x 1, so then how many leaves will I have? I will have LF minus L 1 many leaves. For the second variable, I will have LF minus L 2 many leaves, okay, because I am looking at the average. So, I just look at the sum divided by n. Okay. So, this is just the average. Now, what is this quantity over here? So, LF is independent of this. So, I can take LF outside. Okay. So, I get LF by n. So, I get sigma 1 minus Li I going from 1 to n. So, this is what, and what is sigma Li? Sigma Li is again nothing but L of F. So, this is L of F by n. Sigma of 1 is n minus L of F. So, what I have is oh no. So, yeah. So, this would be this was not correct. I cannot take. So, what I have is, if I take this outside, it would be n times LF. Yeah. So, n times LF. So, I have this 1 by n outside. So, this would just be L of F minus 1 by n sigma Li. Okay, sigma Li is L of F. So, now I have L of F 1 minus 1 over n. This is what I wanted. So, essentially what I am trying to say is that if I just do not consider this Demorgan's basis, if I take any random restriction, then what I have is L of F 1 minus 1 over m. Now, what I have to show is that if the basis is the Demorgan's basis, then instead of 1, I get a 1.5 factor over here. Okay. So, that is what I want to show. So, to show this, it is exactly equal to, right, because this is the definition of expectation. Well, no, it will be a lower bound because it will be upper bound because, well, no. So, yeah, it's an upper bound. The reason I am saying it's upper bound because is that, see, sometimes the size of the formula might collapse even more, right. I mean, depending on what the restriction is. So, yeah, depending on what that restriction is and what gate you have, sometimes it might lead to a larger collapse. Okay. So, this is just a upper bound, yeah, over here. Put this. consider a minimal formula for f. So, consider a formula which cannot be shortened any further. Okay. Consider the smallest formula for f. So, what we claim is that any xi leaf cannot have a sibling whose subtree contains xi. Okay. So, this is actually quite easy to argue that suppose let us assume that this node is a I have an AND gate and I have a xi leaf over on that AND gate and I have a sibling with a subtree overhead, and suppose somewhere over here I have xi again in that subtree. Okay, so, we will show that this is not possible. Why is it not possible? So, we will look at both the cases when xi takes a value 0 and when xi takes a value 1. Okay. So, what we will argue is that, so if I have an AND gate over here, then without any loss of generality I can set this node to be 1. Okay. So, this node can be set to 1. Why can it be set to 1? Because suppose if xi is 0, if xi is 0, then anyway setting this to 1 or 0 or any value does not matter, because this node evaluates to 0 irrespective of whatever is there on the right hand side, right. And if xi is equal to 1, then I have already set this to 1, right. So, what does that mean? That means that this is not the minimal formula for f. So, because in the minimal formula, because here without any, because if I have a structure like this, then in this structure I can replace this xi with a 1, which means that I am shortening the size of the formula by at least one gate. Okay. So, the assumption that I made, that considered a minimal formula for f, in that minimal formula such a structure cannot be present, and if I have an OR gate, the same argument holds. Okay. So, this is the, it is kind of a pictorial way of proving this. Okay. So, now I will stop here, anyway I am over time. So, using this idea we will show that how we can count a little more efficiently. Okay. How we can, so here we are just counting just an I mean this is just a very basic way of counting how many nodes get reduced, but with this assumption we will show that how we can give a better upper bound. Yes. Yeah, exactly. Instead of AND, if you have an OR, then you just set xi to 0 in the subtree. Okay. So, anything else?